Today we are going to present to you our nano-satellite attitude determination and control system. We are doing this project because of the rising popularity of nano-satellite. We model the nano-satellite to three parts. One is ground station, communication in between, and the nano-satellite itself. Our focus will be on our attitude determination and control system. We're using 9-degree IMU sensors to gather data and pass to our microprocessor, going through a series of calculations, including common filter, complementary filter, and the servo algorithm, and ask the servo to change the attitude, the orientation of the nanosatellite to a desired position. At the same time, the orientation data will be passed to our ground station 3D GUI. From the 3D GUI, you can see orientation of the nanosatellite on space. Therefore, we know whether the satellite is at a correct position or not. However, sometimes we need the nanosatellite to have a special task, so we want a manual control. Now we come to a manual control mode. For manual control mode, we can key in a desired position from a keypad, then the information passed to our microprocessor and transmit to our nanosatellite to our XP. Now we will start our real demonstration. For our nanosatellite, we design, yeah, maybe we move to here.
That is nanosatellite. It's a rover, right?
It's a WE. Our design is like WE. First, right, we design our nanosatellite to observe the Earth. It can collect data from the Earth. That's why the two eyes were always pointed to Singapore.
Oh.
So now I will pass the time to our space manager, Binker, to start the demonstration on space.
Now you can see the two eyes are always pointing to Singapore. And I think in the future, these two eyes will replace by the two cameras, and it can get data from Singapore. And when the nanosatellite is launched and it gets into its steady state, it will count into the ADCS. And this nanosatellite can communication with the ground station GUI. You can always check the status of this nanosatellite from that GUI.
How is it done?
Use XP. Use XP to communicate with communication.
Yeah, wireless.
Wireless.
It's not connected.
You connect here?
It's not connected.
It's used wireless.
The wireless RF.
Yeah.
XB or what is it?
Yeah.
XB.
XP.
XB.
XP, we are using XP to achieve the wireless communication.
Okay, now it's done.
Observe its orientation from our ground station. Now you can see, right? Steady rectangular is there. It means it's a desired position. Now an external disturbance will come in. You can see the eye change direction, also the rectangular change, and it will finally go back to its original position.
Okay, basically what you need to do is, even if this changes, this should go back.
Yes, it will always go back to Singapore. Yes.
And then, are you using common filter there?
You mean the sensor we are using, right? We are using
IMU. And the IMU output is filtered through common filter.
and a complementary filter.
Okay.
Another
What is that
direction.
complementary filter?
What is complementary filter? Complementary filter is we give a designed presentation of the, for example, which sensor we charge more. It's a much simple one compared to common filter. It's just, for example, if common filter, something happened to common filter, it didn't function, then we use this filter. So see, two filter is working together.
If common filter goes, that is algorithm. But IMU has the bias problem. How did you take care of it?
We do the calibration first.
Yeah, but you need to calibrate against what?
Sorry.
Calibrate against what?
Against the original position, the first position. Yeah.
So once you leave it like that, it should run like that. Typically, people use GPS to really.
Yeah. Okay.
So I don't know why you didn't use GPS.
Because due to the budget constraint, right?
That's easy.
But that's true because we only gave $200 external allowance. But for one GPS, usually it costs around $1,000. So we must fix our project, come to a desired position, and also within our budget. That's why maybe just now our Bingo only demonstrates.
Let me ask you one thing. See, okay. This is changing. It's a satellite going up there, it is changing. If this is changing, it will affect this also. Why is it? Is it because of drift that is changing the orientation? You know, he has shown.
Okay.
Is it because of something? Why it is changing its orientation?
Oh, you mean why it's changed orientation? Right? Oh, because there may be some external disturbance, such as some very small planet click our satellite, or maybe because of the pressure, due to some external disturbance.
Okay, so
That's why it
that will not
changed.
affect this.
No, it will not.
So it's attitude determination analysis. Our aim is to make sure the satellite will always point to the desired position, even so maybe something happens in the space we don't know.
Because finally our goal is to observe the Earth. Maybe we want to, due to the currently global warming, we need to know whether the current sea level is high or low. So in the future here will be...
Because my point was, why do you need something of this kind to be reoriented? Why don't you position this? That's why it was, because it's a suspended thing.
Oh, in the future there will be a payload. The payload, because we need desired information from the ground. So as long as we can capture the information accurately, we achieved our goal.
Okay.
Yeah, because this already achieved our goal. That's why, yeah.
So actually the goals I should not ask us.
Okay, now maybe Lino would like to demonstrate more disturbance in all three directions. Okay, you see, right? Even there is a 3-axis disturbance, it still go back to its original. Next disturbance.
Very good.
Oh, that means, right, even the disturbance is continuous disturbance, it still can correct itself. And sometimes we may not only want the data from Singapore, we may need to observe something else. That's why manual control mode comes in.